So now that we have established that the probability that the loss is 0 is equal to 1 minus p, let's figure out what the density of x is on the positive values. So let's write here, let x be greater than 0, then the density of x is, and here we kind of use the good old fact that we know that the density of x can be written as the conditional density of x given n, weighted by the different values of n, summed over n running from 1 to infinity. And the reason why we do not sum this for n equal to 0 is because we have already established what happens in the case where n is equal to 0, because in that case we have that x is equal to 0 and the probability for that is 1 minus p. So we've already taken care of that, and what we're going to look at now is this thing here. So what do we know? What we know is that x is defined as the sum of the n first losses, y1, y2, and so on up to yn. So therefore we have established that x, given that we know n takes a certain value, so given that n takes a certain value, little n, then we know that x is gamma distributed with parameter n comma beta. That was something that was given in the exercise text. And in that case, we then know that the density of x given n is given as the gamma density with these parameters. And the gamma density with these parameters is, well, it is beta to the n divided by gamma of beta multiplied by x to the first parameter minus 1 multiplied by e to the minus second parameter multiplied by x. And of course we need x to be greater than 0, and that's not a problem because we have assumed that here. And plugging in, and also plugging in the point probability for n being equal to n, what we get is n equal to 1 to infinity, so we take the sum, and I enter the beta to the n gamma of beta and x to the n minus 1 multiplied by e to the minus beta x multiplied by 1 minus p multiplied by p to the nth. Now what can I try to notice here? Oh, sorry. I think I just wrote this wrong. It's gamma of the first parameter, so it's gamma of n and gamma of n. Great. Okay, so what can I then notice here? Well, first of all, there are some things that I can take outside of the sum, so at least I can start there. Which things do not depend on n? Well, I have e to the minus beta x, and I have 1 minus p, so I can take that outside of the sum. Inside the sum, what I have left is beta to the n multiplied by x to the n minus 1 multiplied by p to the n, and I divide by gamma of n. And what we really want to do now is we really want to get rid of this sum. And the question now is, how do we get rid of this sum? How do we get rid of this sum here? Now, one thing that we might notice is we're summing over a lot of things to the nth power. And that sort of reminds us of one series that we know of, a Taylor series, for the expression e to the something. Except that in that Taylor series, what we have is that e to the x is equal to, so if the Taylor series is created around 0, then it is equal to the sum from 0 to infinity of x to the k divided by k factorial, right? So this thing here is probably something that we can use to try and write out this sum. However, we don't have any factorial in this expression. But then we recall, since you're all very diligent students and have memorized everything that is in the book, that gamma of any natural value, so for all n's in the naturals, then gamma of n is equal to n minus 1 factorial. Oh, and that is very, very nice, because we can combine these two to arrive at the fact that e to the minus beta x multiplied by 1 minus p multiplied by this thing here is equal to, so this is still the same, but then what I have inside of the sum is beta to the n over gamma of n minus, so I move the factorial in instead of the gamma function. And this whole thing works because n takes on natural values. And then we have x to the n minus 1, p to the n. And now what we really want to do is we want to be able to use this formula here to rewrite our sum into an exponential expression. And the reason why we can do that is because, well, let me just try and take out beta from the sum and take out p from the sum. Because then what I have left in here will be beta multiplied by x multiplied by p all to the power of n minus 1. And then I divide by n minus 1 factorial. And what I'll do now, instead of writing n equal to 1 in the index, is to write n equal to 0, right? Because essentially what I do here is I actually start the sum in 0 when this thing is in minus 1. So when I do that, when I start the sum in 0 instead of 1, then I can also change these values into n instead of n minus 1. So if you didn't really follow, I don't know why I wrote n minus 1 like that. Okay, so if you didn't really follow what went on here, just try to write this down on a piece of paper and really think about it, because it's one of those things that kind of require a little brain gymnastics, but you'll get it, so it's not that hard, luckily. So what I have now here is something to the nth power over n factorial, sum for n going from 0 to infinity. And that is in fact equal to e to the something. So in conclusion, what I get is e to the minus beta x here multiplied by e to the beta x p. And I can collapse these two into one expression. So I have 1 minus p beta p, and then I have e to the minus 1 minus p beta x. And this is the density for x when we consider values greater than 0.